Happy Friday and welcome to CIRCA's research webinar series. Today we are finalizing the first week of our research webinar series with Dr. Chang Liu's research. You may recognize him from his previous work with CIRCA to define the Long Island Sound model. Dr. Liu is actually a marine scientist, and his research interests include coastal ocean and marine ecosystem modeling with an emphasis on the computational and statistical approaches. Just before starting the presentation, a couple of webinar logistics. You're all muted, and please type any of your questions to chat box or Q&A box to sending to all the panelists so we can all see your questions. And at the end of the presentation, we are trying to come into most of them and cover the major elements in the Q&A or chat box. So without further ado, Dr. Liu, the floor is yours.
Okay, thank you, Yaprak, for the introduction, and thank you, Katie, for organizing and setting the webinar up. And thank you, everyone, for joining the webinar. Today, I'll be talking about modeling nearshore dynamics of extreme storms in Connecticut. This is recent work at CIRCA conducted by me and my co-authors, Yaprak, Yan, and Jim. And just a little background information to start with. So flood hazard planning requires accurate estimation of total water level elevation due to predicted tide, surge, and wave runoff to design flood protection structures and improve coastal risk planning for severe storms. And the coastal topography, meaning the shape of the coastal area that includes both above and below water, and also the nearshore hydrodynamic conditions or circulation patterns can impact the flood mapping in our complex environments. So some existing approaches have shortcomings in a few ways, including like using a simplistic bathtub approaches, and also with insufficient spatial resolutions in the model or lack of a comprehensive model physics. Someone could also fail to calibrate or validate their model with the real measurement data. And some also didn't consider the sea level rise, the impact of sea level rise to flooding. A few examples of the existing flood map products that includes Connecticut. First one is the FEMA insurance flood map. This one is very commonly used to determine flood, whether a building or structure is inside the flood zone, and also determine the flood insurance rate. In Connecticut, however, the wave circulation, the wave calculation is based on empirical equations along the very coarse transect lines. And the second one, NACCS, which is North Atlantic Coast Comprehensive Study. This is based on the model simulation of hundreds of synthetic extreme storm events, and then based on that calculate the future flooding scenario under, say, 100 or 500 years. And along the coast of Connecticut, the horizontal resolution is approximately from 0.5 mile to 1 mile here. And the third one is developed here at CIRCA based on the FVCOM-SWAVE ocean model. This one covers the whole Long Island Sound, and we simulated over 50 historic strong storms, and based on these simulations, we compile the projections for the future scenarios, including from 10-year to 100-year return interval scenarios. So these three products will be a baseline to compare our current work with. And the objectives for this current study, firstly, we're going to create an accurate flood maps by applying a high-resolution wave model to the nearshore areas in coastal Connecticut, including Branford, Norwalk, New Haven, and Fairfield, to determine the total water elevation. And secondly, we're going to use a validated model. We're going to validate the model using high water mark observations during Superstorm Sandy, as well as wave observations made inside the New Haven harbor. And thirdly, we're going to use a validated model to assess the storm with 1% and 10% annual exceedance probability, which correspond to 100-year and 10-year return intervals respectively. So a little more explanation on the AEP, or annual exceedance probability. So that's the probability that an extreme storm occurs annually. So 1% corresponds to a 100-year storm. So the lower the number is, the rarer the event will be. And here are the bathymetric maps of the model domain here. We included Norwalk, New Haven, Branford, and Fairfield in this work. And all of these, the red and blue points inside the map indicate a max total water level measurement taken during Hurricane Sandy that we will compare our modeled results with. So for the model setup, we use FUNWAVE-TVD, which is a piece of computer program that can wave coastal waves at the phase level. That means the model considers more wave physics, including diffraction, refraction, and reflection, than many other types of models. And in FUNWAVE model, we can specify, we can place a virtual wave maker like is shown in this red bar in this figure here. So the wave is generated at the wave maker with specified wave height, frequency, and wave direction to generate wave in the model domain. And for our work, we use a grid resolution of 2 meters, approximately 6.5 feet, which is fairly small. And we're gonna use the model to simulate 1% and 10% AEP scenarios. So as I mentioned before, we validated the model with the comparison to the measured high water marks during Sandy. So here are the results comparison plots here. The horizontal axis is the measured high water mark, and the vertical axis is the model total water level. The dashed line is a one-to-one line, and each data point here corresponds to a measurement at a location that I showed 2 slides ago. So the closer the point is to the dashed line, indicating better model performance. So overall, the agreement is pretty good. For the 3 areas, Branford, Norwalk, and New Haven, the overall root mean square error is only 1/4 of a meter. And for Fairfield is 0.38 meters. And most of the comparison falls within the 10% margin of relative error. So, and the second validation exercise we did was to compare the wave height measurement. So in the year 2015, 2 ADCP equipments that measure significant wave height were deployed in front of and behind the New Haven breakwaters. So we set up FUNWAVE simulations that we used measured wave characteristics observed at NH1 to force a model, and then we compare the observed and the modeled wave height at NH2. As you can see, the numbers are in agreement, indicating that the validation of the model physics, nearshore wave dynamics, including wave propagation, refraction, and diffusion, are confident. So now we are confident with the model setup, and then we assess the projected 100-year scenario flooding maps with the existing products. Firstly, we compare with FEMA. So for in these three areas, the FUNWAVE results here on the left and on the bottom here. From these we can observe that. So I apologize for the small words in the legend, but with the color you can see indicates the lighter the color is, the higher the total water level. So from the FUNWAVE results, we can see that the wave diffracts and lose energy when propagating from the deeper areas into nearshore shallow areas. And also the total water level in general is higher for FEMA than our FUNWAVE results. And especially we take a closer look at the Norwalk here. So FUNWAVE on the left, FEMA on the right. And the difference here is nearly 2 meters along the coast. And it appears that the FEMA does not consider the island diffraction of the wave. That could explain the difference between the two scenarios here. And the second one, we compare the FUNWAVE flood extent map, which is yellow here, with the NACCS 100-year flood map, which is blue. So we found that NACCS overestimate surge water level, but underestimate wave heights. And that could result in an overestimation of the flood extent. For example, in these two areas where in the NACCS map it shows being flooded, but not in the FUNWAVE maps. So because NACCS has a larger spatial scale, as I mentioned, from 0.5 mile to 1 mile, and it was not designed to incorporate nearshore wave dynamics, like fine scale model physics as well. That we believe is what's causing the discrepancy here. And thirdly, we compare with our own FVCOM-SWAVE results here. So the FUNWAVE is red and the blue is the FVCOM 100-year maps. Because for FUNWAVE, we use the same surge water level and wave height from FVCOM as a boundary condition to force the model. And with the implementation of FUNWAVE, it introduces a finer spatial scale and more comprehensive nearshore dynamics. We could capture the wave runup that could potentially lead to a larger flood extent, as we see here. Like the extent in red is slightly larger than the blue ones. So the development of the FUNWAVE modeling is an improvement over the existing FVCOM-SWAVE model products to bring the more accurate estimation nearshore. And now we can consider the sea level rise scenario here, because in Connecticut it was projected a sea level rise of 20 inches or half a meter by year 2050. So we compare a scenario where there's a 10-year extreme storm with the 20-inch sea level rise with the 100-year storm events. So as you can see, there is very little difference in the flood extent between these two, indicating that what we consider a 100-year storm today would be very similar to a 10-year storm by 2050 because of the sea level rise. That is also to say that the sea level rise will increase the frequency of extreme storm flooding, because the total water level with sea level rise of a 10-year storm will be comparable to what we now consider as a 100-year storm. Okay, to summarize what I talked about today, firstly, the FUNWAVE model. We believe models of wave processes more accurately in shallow water regions compared to the existing model products and the flood map products. And secondly, we also examined the local sea level rise of 100-year and 10-year scenarios, and found that the flood extent of the two storms showed very little to no difference in our complex topography due to sea level rise. And thirdly, we suggest planning approaches consider the increase in the frequency of the storms in predicting the flood zones due to sea level rise. And this is the end of my presentation. I would like to take any questions you have. Thank you.
Thank you, Dr. Liu. So now I'm looking for the questions on the chat box. And so there's a general theme about like the comparison between FUNWAVE results and the FEMA results. If you can maybe go for them a little bit more. And the questions generally indicate that where does this difference is coming from with the FEMA results, and then is the FEMA results are over or underestimating compared to the FUNWAVE results?
So we can see here the FEMA in general is overestimating the total water level, or the BFE in their terminology. Because of the methodology, it's based on, like, they did the calculation along transects that's fairly far apart from each other. And then in between, I believe it's based on the spatial interpolation, which apparently cannot resolve fine scale variations. However, our model resolution is 2 meters, and we have the phase resolving numerics that includes more model physics. So we believe the methodology differences is leading to the difference in the water level estimations.
Can you please also remind everybody like the lighter colors, what lighter colors indicate and the darker colors indicate between the two
So
images?
the lighter color means high water level. Like show here, the yellow one is greater than 5.5 meters. And the darker blue means lower water level. The darkest blue here is below 3.5 meters.
Thank you. Hopefully this will clarify for some folks on the chat. So another question is about like, have you included any tidal range or like river flows in this model?
We did not include rivers in this model, and for tides, we did not include like the astronomical tide or like the tidal variation. But to simulate that, we included the total surge level that is simulated using FVCOM and including the both tides and storm surge, the peak surge level during Hurricane Sandy.
Okay, thank you. CIRCA's previous model, how is that different? This new model how is that different from the CIRCA's previous flooding model?
Okay, so the previous CIRCA model is a FVCOM-SWAVE, which is a more larger scales, cover the whole Long Island Sound, and is focused on the whole Connecticut scale. And by using the FUNWAVE model, we can further improve, like bringing the results already produced using FVCOM to a finer scale, nearshore scale, to get a better, more accurate predictions nearshore in a smaller scale.
Mm-hmm. Just to add to your comment, the previous results were coming up to, they were in coarser resolution, and they were mostly in the offshore areas, the results, and reflected on the inland. And this model is like, since it's focusing on a smaller region, it gives like much more accurate wave definition and the surge levels. So another question is, all right, so why cannot we apply this model to whole Connecticut shoreline and only just like apply it on the specific towns?
So the biggest obstacle is the computation time, because the FUNWAVE, we have very fine resolution of 2 meters, and it's very computationally expensive. For example, to run the New Haven one, it takes about a week to run just one town under one scenario. So at the moment, we wouldn't consider it very viable to apply to the whole Connecticut. It's for resolving such a fine scale, I think it's more economic to do it in the town or city scale.
Okay, so another question is, are you also able to model a 100-year return interval using expected 2050 conditions, sea level rise, storm frequency? If today's 100-year storm are going to be a 10-year storm in 2050, what would a 100-year storm would look like in the future conditions?
We haven't performed the model run for 100-year with sea level rise yet, but it should be straightforward to set up, and as soon as we've done that, I believe we can make that public.
Yeah. Yes. Are there any other applications that you know of FUNWAVE in different places?
Yes, there are different places it's being applied in coastal Rhode Island for similar purposes, like nearshore flood modeling. It was also used at a larger, like ocean basin scale, to model tsunami waves that I have learned, although I was not too familiar with the details, but it has many applications.
Dr. Liu, can you also explain what are the some of the reasons that the specific locations are choosing to do the FUNWAVE simulation? Like New Haven, Norwalk, Branford, Fairfield. I can answer to that actually. Because these places are very complex environments. So in New Haven, there are like 2 outside offshore breakwaters, which actually creates how the waves are moving inside the bay that require like higher resolution. Like the slide that you can see, there are some places that's over and under flow that we wanted to know in more detail. Norwalk has an island chain that also affects this kind of a wave propagation that can impact like how much the flooding extent can change. And Branford is like very heavily focused on like the marsh system close with like the road structure. So it would be important for us to know like how much would be the wave overtopping on the road lines. So so these are that's why the title of this talk is like complex coastal environments. So we can do a little bit more in-depth research on that. And
yes.
Yeah, I'm looking for. Okay, that seems like these are all the questions so far. And if you have any other questions, that you can reach us through Dr. Liu's email, my email, or circa@ucon.edu. And we can now remind you our future. Yeah, I can now share my screen. So if you would like to learn more about Dr. Liu's research, you can go and look at this like simple fact sheet. We have prepared a journal article that is soon to be published and will be available and be informed to all the resilient Roundup sign-up people and also to you. And just a reminder for our next presentation on Monday, it's going to be about the extreme precipitation and riverine flood risk from Dr. Xinyi Shen, and we are waiting for you to join us on Monday again. Thank you so much for joining and listening to us, and happy Friday and happy weekend.